Hi everyone, I'm gonna be presenting our deep learning group projects. So I'm presenting behalf of my groups. So our topic is focused on developing a multi-height fine-tuning CNN model, which is for an classification, especially targeting a different cat breeds. Okay, moving on, here's our project's overviews and goals. So our main goal was to build and compare image classification models that are accurately identify specific cat breeds, for example, like Burmans, Siamese, and Ragdolls, while also still maintaining a general image recognition abilities. So here we're gonna introduce a multi-height fine-tuning architecture that will allow the model to handle both specifics and general image effectively. So in here, we're gonna compare at least two pre-trained CNNs to see how well each performs under the new setups. Okay, so next will be our custom datasets and details. So here, like I mentioned earlier, we're gonna focus on three target classes. First is the Burman, second is the Siamese, and lastly we have Ragdolls. Our datasets include over 2,400 training image, so about 800 for each classes. So here we're gonna set aside for 20% for this data for of this data for validations and around 250 separated image for testing. So for with this, so this will be balance the setups, help ensure the fair and accurate model evaluations. So moving on, here is our data pre-processing and argument. So here to prepare the data, so every image we're gonna resize it to 224 and by 224 pixels, and we're gonna normalize it by using the ImageNet means and standard deviations. So here we also apply the random transformation, uh, especially the random resize crops and the random horizontal flips, which is with the zero point 0.6 probabilities. So here the goal is to increase the dataset varieties and reduce the overfittings, which help the models learn to recognize cat even with the slightly different poses or lightning. So next is our model selection and architecture. Here we're gonna be talking about the pre-trained model first. Okay, so to test the architecture, and so we're gonna be using our two pre-trained CNNs. First is our ResNet 50 is known for its high accuracy and deep structure. Second is our MobileNet V2, which is known for lightweight and efficiency. So we want to compare the trade-off between the performance and the efficiency, like the accurate versus the speed and size. So next is our architecture overview. So here where our modules become a bit unique. So we're gonna be using our pre-trained CNN backbones like I mentioned earlier, for example, the ResNet 50 and kept the original ImageNet classification height frozen. Now, then we're gonna add the new height called the cat height that focus only on the three cat breeds. During the inference, if the cat height confidence is higher than zero point 0.6, it will take the priorities. Other model rely on the original ImageNet height. So this makes the system flexible, accurate on the cat, but still capable of identifying other objects. Now, moving on, we'll be talking about the experiment setups and training strategy. Here we're gonna be telling the training details. So first, I'll be telling in the first training stage, we call the feature extractions. We froze the entire pre-trained backbones and the original classification heads. So we only train the new cat head using the Adam optimizer with a learning rate of 1e minus 3. The step follow the new layer to adapt quickly to our cat's data without disturbing the general ImageNet features. Now moving on to the second stage. So this is second stage we call the fine tuning. So we unfroze the part of the backbone, specifically the layer 4 in the ResNet model, and train it again using a smaller learning rate of the 1e-5. This allowed the model to refine its deeper layer for cat recognitions. It will improve the accuracy without causing instabilities. Now, moving on here, we'll be talking about the training management. So to make the training stable and reliable, we use two techniques. First, the early stopping, which is stop the training when validation performance stop improving. So with the patient, which is set to 5 epoch, okay, which is like I show in the slide, we set it at 5. So here the second is the model checkpoints. So where the models only saved it weight when the validation accuracy reached the new best value. This ensure that we don't overtrain it, and that's only the best model. That only we sure that we use the best model to use for the testing. Okay.
So to start off, we import everything that we need here, followed by checking if GPU is available. If it's not, then we will be using the CPU. And these are the directories of train and test datasets that we'll be using. Next step is to prepare by resizing the images here, because like all of the pictures are like in different sizes. We want them to be in the same size to feed into the models, so we will transform it here. And we also put the labels and indexes on each cat's class. So for example, Burman will be 0, Ragdoll will be 1, and Siamese be 2, to identify them from each other and like separate them. This is a custom data set created just solely for validations data set. And the evaluate here will be used as a function to calculate the average loss, average accuracy, and so on. So for here, you can see that there's 20% for validation, which is 0.2, which means that, for example, if there's like 1,000 pictures in the data set, 200 of them will be used for validations, and we use random shuffle indices to like shuffle the pictures along, so it will not be in linear, and the pictures that the model selected will be randomized. These are just to get path, and as you can see here, it's the custom data set that we created before. So we input like the data, the images and stuff for validations and for training test. For this code, we will be using the mobile net. However, the ResNet will be similar to this, literally the same intricate structures, but there are some slight differences in loading the models in. So as you can see, we'll try using the newer models. If it doesn't work, then we'll go back to older versions. Now, here, since the model is currently in single head model, we're trying to implement it into a multi-head model, so for better performances as well, which is this class comes in. And to save the model automatically after training is this function. So, alright, here you go. So basically, if the path does not exist, we will create a new path name. I mean, not path name, PTH name, PyTorch file. This will be to save the current weight of the model, and we also need to save the classes, which will be stored as JSON files right here. So for the next time when the model is loaded, right, the next time that you want to use the already fine-tuned model, you can just call the current model and load the checkpoint of the weights and the classes that was already saved by importing them into it, and the model will already be fine-tuned. So it will be saving resources, as you don't need to like fine-tune the models every time that you run the code. These are for URL images which were not used anymore. Okay, so to the predicting, this one here is for predictions of the pictures that we have on hands. So predict the image batches, which is for the test data set. Now you can see, since we already have the multi-head model, these were not used, since these are for the URL uploading, and we do not use that anymore. There will be a main loop for it around here for our own test. So these are for right. So these are for prediction before fine-tuning the model. It will give out answers before like fine-tuning itself in a form some sort like this. One moment. Some sort like this, where it will show the confidence level of the model and the predicted pictures, and also whether it's correct or not. So for example, the first picture predicts Siamese and it's actually Siamese, and so on. You can see it predicted links, but the true value is actually ragdoll, which means that it's wrong. Anyway, moving on to actual fine-tuning itself. The true epoch here is actually 70. We're not using 2 is too low, so we limit to 70, which means that if the model could work up to 70 epochs max, but it will stop beforehand, since we have the patient's file will be explained later on. So basically the max epochs available is 70. And for the here is the main training loop. You can see we calculates the training average loss accuracy, and the validation accuracy loss will be using the function evaluate on, which were defined above. And you can see we use cross entropy loss with learning rate of 1 e to the power of -3. These here are the main training loops, which will follows the number of all the epochs available. So it is in the range of the epochs. This here, just to put it into the graph, will be used later on to show the values. And here is to save the model. We have some sort of penalty system, as we said that we use the patients up to 5. So if the model does not improve, for example, the model works up to, let's say, epoch 3, and if it does not improve in epoch 4, the model will save here, and the epoch 4 models will not be saved, and the penalty of patients will be +1, or the no improve here, you can see will be +1. So on to number 5, 6. If it's yet to improve, keep plussing up the penalty. And the models that were used to calculate for epoch 5 and 6 are the same as the model 3, since it is the best, until something is better, let's say epoch 7 is better than epoch 3, then it will save here instead, and then continue, and then cancel this and continue the loop again. So let's say up until epoch 12, which is up after 5, it has yet to improve, then it will cancel this and still use the epoch 7 models as it is the best model possible that we could train. That's how the penalty system works with no improve here with the patience of 5. You could improve the patience. I mean, you could increase the patience to something else. But I feel like 5 would be the best as it could save the resources that we used. We also freeze and unfreeze the model. We unfreeze to like overwrite the model to the ones that we want to save, and we freeze it to like not mess with the older original models when the epoch is worse. I mean the value, the performance is worse than the last epoch. So this is for the URL, it doesn't matter. But here, this is prediction after fine tuning. So, and it will show the same results as like the ones before, like this. It will be in the same type of, output. So you can see here, and the output will be similar, whereas Siamese, it will show true, the actual true value is Berman, but you can see the confidence level is spiked up. And these is for graphs. So the graphs output will be something similar to this, which I will be putting it in Google Colab. And you can see how many epochs were ran since we outputted as well. Let's see, after epoch 12, this is for ResNet model. After epoch 12, up to epoch 17, you can see that the validation loss is slightly better, but not up to the point where it should be saved, because it is not much difference from the ones on epoch 12, which is why after epoch 5, after 5 epochs, we cancel the run loop and saving the epoch 12 to be used later on. That's pretty much it for the coding part, and I'll be explaining how to use the CNN for now. Okay, so in the Google Colab, this is the entire code for professor to read the results that we pasted in. These are to call the model itself. So you just click run. After it finished running, you can upload the picture of a cat itself. Let's say ragdoll cats here. And then copy the file path, put it in the predict loop. And then the model will be able to predict. Can also change to ResNet model if you want. You can see the confidence level right now is 0.88. But if we run on ResNet model, you can see that the confidence boosts up to 1. This is after fine tunes. So we call the model with using Hugging Face right here with the PyTorch and JSON file.
Now, moving on to the results and analysis. So here is the before tuning of the ResNet 50. This one is this slide show the the predictions from the ResNet 50 before fine tuning. Okay, as you can see here, it's not really consistency, accuracy, and it was decent but not ideal for detailing cat breeds recognitions. For example, here you can see that let's look at the first row on on the commands that we get here, not the on the pictures one, not the virtualized one, on the raw answer that we have here. First, we have the Siamese cat. We have it. We then moving on here, we also have the probabilities of the confidence rate that we have, uh, and also we have the the true and the actual answer, which is true, and also it's Siamese. But if we looked at the column on the second columns, here is guessed that it's links, but it's not actually links. But which you can see that the model is also not confidence on it. We can see that the confidence score is just 0 0.2, which you can see that it's really not links, it's fractal. Okay, so here was the before fine tuning, you can see, and also there's some errors in the pictures. Moving on, here will be next is after fine tuning. So after the fine tuning of the ResNet 50 is improved significantly, the predictions became much more confident and correct. This demonstrates that the fine tuning, even a small portion of the backbone, can greatly improve the performance on custom datasets. As you can see on the result, we can see that it's more accuracy now, and it gets it with the much better confidence score. Now here will be next. This is the graph. Okay, this is the slide that show more example of the fine tuning of the ResNet 50. So we can see how the model correctly identify categories showing strong specialized another our target classes while maintaining stable generalizes. Okay, now next we'll be moving on to the second model, which is mobile net v2. So here you can see the sample with the mobile net v2 before the fine tuning. The mobile net v2 started with a low accuracy as expected since it's smaller and faster model. However, it performed reasonably well given its lightweight structure. So same goes like the for same as the ResNet 50 before fine tuning. This one is mobile net v2. This one also have the confidence score which is low, and some of it is also wrong. So we're gonna have a look at after we fine tune it. So here, moving on, here is the fine tune of the mobile net v2. We can see that after the fine tuning, the mobile net v2 show clear improvement here. It predicts become more stable and accuracy increase, though it's still slightly below the ResNet 50. So this proves that the compact model can benefit from our two-stage training methods. Okay, next will be more result on the mobile net v2. So here is the image that we present is using the fine tune of the mobile net v2. We can see that while not perfect, it maintained the consistent prediction with faster inference times, which makes it practical for real-time or mobile applications. Next is the result and analysis. Here is the comparison table. You can see that the ResNet reaches it 93% taste accuracy and highest validation accuracy of the 92.34%. Also here, the mobile net v2 achieved just 88% tape accuracy and 88.41 validation accuracy. Also, however, the mobile net v2 is much smaller, only 3.5 million parameter compared to the ResNet, which have 25.6 million. So depends on the use case. Both models have strong points. ResNet for accuracy and MobileNet for speed. Now, next, moving on is our conclusion part. Okay, to conclude, our experiments show that the multi-head fine-tuned architecture work effectively across the different CNN backbone. The first model, ResNet 50, achieved the highest accuracy, while model V2 provided better efficiency and faster inference. This approach balances specializations and generalization, meaning the model can focus on cat without losing its ability to recognize other objects. So on here, to add on, the best model I can which I can choose is the model Net V2, since it's a small it's a small architecture, but it's still having a high score, not not that low, not that far apart from the ResNet 50. So I think it's more practical in real life. So overall, here is our project demonstrate how to combine the pre-trained model with a smart fine tuning can lead to stronger and adapt performance. So that's all for our presentation. Okay, thank you so much for listening and for your attention. Thank you.